Okay. Next one. Example. Purple, of course. Summation 1 over n to the power of p. Okay, where p is some real number. P is a real number. Okay, so we want to know when does this converge for which values of p? So I look at the integral of 1 over x to the p dx from 1 to infinity, which is improper, of course. And 1 over x to the p is the same as x to the minus p. So what do I get? Do my integral, I get negative p plus 1, right? Over negative p plus 1 from 1 to t. I get this sort of awful thing. Limit t to negative p plus 1 all over, let's write that as 1 minus p, minus 1 over 1 minus p. Okay, I made an assumption here. I made an assumption here that p is not 1, right? Where did I make that assumption? Right here. Okay, p is not equal to 1. Let's say here, right here, if p is equal to 1, then we have, we have this integral. So divergent in that case, certainly. We did that above. Okay, returning to my calculation in black. So t is going to infinity. So I have to analyze this thing. Okay, so t is going to infinity. When is this expression here going to yield a finite number? Well, I'm going to need that t to be downstairs, not upstairs, right? So I'm going to need the exponent. Let's write this here. I need the exponent to actually be negative. Negative p plus 1 has to be negative. If that's negative, then this t here will end up downstairs. And when t goes to infinity, the expression will become 0. Okay, otherwise you have t upstairs, and then the fraction here will go to infinity. So I'll write it like that. I need the negative p plus 1 to be less than 0 for convergence. Therefore, summation 1 to be converges for p bigger than 1. And diverges otherwise. As if p is equal to 1, you're in this scenario over on the left here. And if p is less than 1, then as I said, this t here stays in the numerator. And when you take the limit, you get infinity.